औज़ुबिल्लाहिमिनश्शैतानिर्रजीम बिस्मिल्लाहिर्रहमानिर्रहीम। अस्सलाम वालेकुम क्लास। उम्मीद है आप सब ठीक ठाक होंगे, खैरियत से होंगे। This is lecture number 14 for the course of partial differential equation. In our previous lecture, we have discussed about the Laplace equation. We have divided the Laplace equation into four different simpler problems. Uh, we have also solved one simple problem from that Laplace equation. In this lecture, we will solve the remaining parts of the problems and construct a complete solution of the Laplace equation. So, without going into details, let's consider the second problem of the Laplace equation, which is del square u1 is equal to 0. U1 at x0 is equal to f1 of x. U1 at x and y is equal to h is equal to 0. U1 at 0 and y is equal to 0, and U1 at L and y is equal to 0. This is the one of the second problem among all those four problems. तो इसके सोल्यूशन के लिए भी हमने सेपरेशन ऑफ वेरिएबल्स का जो टेक्निक है वो यूटिलाइज करना है. वी विल अज्यूम दैट द सोल्यूशन ऑफ द प्रॉब्लम एग्जिस्ट and the solution can be written in the form of product of two functions: a function of x, which we represented by h of x, and a function of y, which we represented by pi of y. So using this estimate, we will try to find some analytical shape of u1 of x which satisfy this partial differential equations and all those boundary conditions. So based on this assumption, we can find the second derivative of u1 with respect to x is h double prime of x into phi of y. Similarly, the second derivative of u1 with respect to y is h of x into pi double prime of y. We know that the u1 is the solution to the Laplace problem. This is not u4, make some necessary correction, this is u1. We know that u1 satisfy this partial differential equation, so if we substitute these estimates into this PD, we will get two ordinary differential equations. So substituting the values of second derivative of x and second derivative of, with respect to y, we get h double prime of x multiplied by pi of y plus h of x multiplied by phi double prime of y is equal to 0. After a short algebraic manipulation, we can find that h double prime of x divided by minus h of x is equal to pi double prime of y divided by pi of y is equal to minus lambda is equivalent to some constant. And the reason behind this equality is because there is only one possibility for two functions to be equivalent to a constant. A function of x cannot be equivalent to a function of y unless they are both constant. So we will put the negative sign here with h double prime of x, and the reason behind this is because we have two conditions for y, for h. So so we will use negative sign in the left hand side of this equality. So this is basically two different equations. The first equation tells us h double prime divided by h is equivalent to minus lambda, and the second part of this equality tells us pi double prime divided by pi is equal to lambda. Now what does the boundary condition says us? The boundary conditions are u at x is equal to 0 and y is equal to 0. This tells us h at 0 and pi at y is equal to 0. This the first equation does not give us any information about h at 0. We cannot say that h at 0 is equivalent to 0, because if h at 0 is equal to uh, mm, uh, the second identity tells us h at L is equal to pi at y is equal to 0. The third identity tells us h of x is equal to multiplied by pi f at 0 is equal to f of f1 of x, and the fourth conditions, which is this one, tells us h at x into pi at h is equal to 0. So um, three of these relations are informative and one relation is not informative. This relation does not give us any information. This relation tells h multiplied by phi at 0 is equal to some non-zero quantity f1 of x. We cannot conclude that pi of 0 is equal to 0. uh, okay, and these three conditions are very informative for us. These three conditions tells us h at 0 s0, h at l s0, pi at h is equal to 0. So basically we have two conditions for the differential equation in x and one condition for the differential equation in y. So considering the first equation, we see that h double dash divided by h is equal to minus lambda, which can be formulated as h double prime plus lambda h is equal to 0. We can combine these boundary conditions also. So we have a complete set of second order boundary value problem. Now we will use the method of auxiliary function to solve the second order ordinary differential equation. The auxiliary function associated with this ODE is m square plus lambda is equal to 0, which gives us the which gives us two roots which are basically imaginary, plus under the root lambda iota minus under the root lambda iota. Now if the roots are imaginary, then the solution have a special shape cos under the root lambda x plus c2 sine under the root lambda x. So we will write h of x is equal to c1 cos under the root lambda x plus c2 sine under the root lambda x. Now this is two parametric family of solution, and this function satisfy the uh, differential equation part of the problem. The solution must also satisfy these two conditions. So we will impose the first condition, h at 0 is equal to 0. uh, we get h at 0 is equal to c1 cos under the root phi under the root lambda into 0 plus c2 sine under the root lambda into 0, which can be concluded as c1 is equal to 0. If we fix c1 is equal to 0, then h of 0 is of course 0. So if c1 is 0, we can write h of x is equal to c2 sine under the root lambda x, this equation. अब इस इक्वेशन को जो दूसरी बाउंड्री कंडीशन है वो भी सेटिस्फाई करनी चाहिए, मींस h की l पे जो वैल्यू है वो 0 आनी चाहिए. तो अगर हम यहाँ पर x की जगह l सब्स्टिट्यूट कर देते हैं तो हमें 0 इज इक्वल टू h ऑफ l इज इक्वल टू c2 साइन अंडर द रूट लेमडा मल्टीप्लाइड बाय l. अब यहाँ पे हम अ, दो ही कंडीशंस है हमारे साथ, या तो c2 0 है या जो दूसरा साइन का जो टर्म मल्टीप्लिकेशन में है या वो 0 है. तो c2 को हम 0 नहीं कह सकते, because if c2 is also 0 then we will end up in a trivial solution. So the only possibility with us is that sine under the root lambda into l is 0, which means that under the root lambda must be equivalent to n pi by l. So we have a solution of the form h of x is equal to c2 under the n pi over lx. So basically this solution satisfy the ordinary differential equation uh, and both of the boundary conditions also. If we substitute x is equal to 0, we get 0. If we substitute x is equal to l, we get c2 sine n pi l divided by l means sine n pi, which is always 0. So basically this is one parametric family of solution, and for any value of c2 this function satisfy the complete set of the boundary value problem. Now we will consider the second part of the identity, which tells us phi double prime divided by phi is equal to lambda. Okay, this equation can be formulated in this shape: phi double prime minus lambda phi is equal to 0, and the only condition given with this equation is pi at h is equal to 0. Now we are trying to find a solution which satisfies this ordinary differential equation and this this boundary condition. So which is so much easy. Consider the auxiliary equation of the problem. The auxiliary equations gives you two roots, m is equal to plus minus under the root lambda, which is always real. So if the roots of the auxiliary equations are real, so you can write equation in two ways. You can use the exponential form of the solution, or you can use the cos hyperbolic and sin hyperbolic form of the solution. So here due to some reasons, and the reasons is because we want to calculate a solution which satisfy this boundary condition also. So because of this reason I will use the hyperbolic shape of this solution. So the solution pi of y is a constant d1 multiplied by cos hyperbolic under the root lambda y plus d2 sin hyperbolic under the root lambda y. अब ये भी टू पैरामीट्रिक फैमिली ऑफ सॉल्यूशंस है। d1 और d2 की कोई भी वैल्यू अगर हम यूज करेंगे तो ये जो सॉल्यूशन है हमारा वो बाउंड्री वैल्यू प्रॉब्लम सेटिस्फाई करेगा। इसमें जो लेमडा की वैल्यूज है वो अगर हम यूज कर ले तो सोल्यूशन पाई एट वाई हमारे साथ बनेगा डी वन काज हाइपरबॉलिक एन पाई ओवर एल वाई प्लस डी टू साइन हाइपरबॉलिक एन पाई ओवर एल वाई। जिस तरह से हमने प्रीवियस स्टेप में किया था कि दिस सॉल्यूशन मस्ट satisfy pi at h is equal to 0. If we apply this condition directly onto this solution, we will get we will not get any information. Okay, so we will use the translated version of this solution. We will replace y by y minus h. Note that in our previous case we have replaced x by x minus l, and the reason was that we have pi at l is equal to 0. Now we have pi at h is equal to 0, so we will replace y by y minus h. So replacing y by y minus h, we have a general shape of the solution as in the equation pi at y is equal to d1 multiplied by cos hyperbolic n pi over l y minus h plus d2 sin hyperbolic n pi over l into y minus h. Now we can apply this condition over uh, this equality. We can apply this condition. Okay, so on the application of this condition, we get pi at h is equal to d1 cos hyperbolic h minus h and d2 sin hyperbolic h minus h. Sin hyperbolic is always 0. So we get cos hyperbolic 0 is equal to 1, so we get d1 is equal to 0. So if we fix d1 is equal to 0, our solution becomes pi at y is equal to d2 sin hyperbolic n pi over l into y minus h. Now this solution satisfy this ordinary differential equation and this boundary condition. You can verify it by substitution. Okay, so I will write the solution u1 is equal to h of x, which is cn sin n pi over lx multiplied by pi of h pi of y, which is dn multiplied by sin hyperbolic n pi over l into y minus h. Okay, so combining now look here, there are two constants cn and dn. It looks like they are two different constants, but in fact their product is also a constant. So we will write cn multiplied by dn is equal to an. Okay, so we have a compact shape. A compact form of the solution is u1 n of xy is equal to an multiplied by sin n pi over lx multiplied by sin hyperbolic n pi over l into y minus h. This is basically uh, infinite families of solution. For n is equal to 1, this is also solution to the problem. For n is equal to 2, this is also a solution to the problem. And the special thing in this solution is this solution satisfy this partial differential equation and all the zero boundaries condition. ये तीनों conditions भी ये satisfy कर रहा है। अब हमें जो ए एन है वो इस तरह सेलेक्ट करने हैं कि जो हमारा सोल्यूशन है u1 ऑफ x वो इस इनिशियल कंडीशन को भी सेटिस्फाई करें। Really speaking, we have to select a n in such a manner that our solution satisfy this condition also. So enforcing this condition over this problem. Now, before going to impose the condition, we have to apply the superposition principle and construct the infinite sums of solution. What does the superposition principle says? The superposition principle say that if u1 u2 are two solutions to a specific linear problem, then their sum u1 plus u2 is also the solution. So here we have infinite solutions to a linear problem. So the sum of all these solutions is also a problem. So we can write u1 of xy is equal to summation n starts from 1 up to infinity, a constant an multiplied by sine n pi x over l multiplied by sine hyperbolic n pi l into y minus h. This is a compact shape of a unique solution. Now we are trying to choose the values a n in such a manner that this solution satisfy the initial condition u1 at x0 is equal to f1x also. So imposing this condition, we get so, means you can substitute y is equal to 0 here and here. So you get u1 at x0 which is equivalent to f1x is equal to summation n starts from 1 up to infinity a n sin n pi x over l into sin hyperbolic n pi over l minus h. Now there are a special two types of constant. One constant is a n and the other constant is sine hyperbolic n pi over l into minus h. This is also a constant quantity. The encircled quantity is also constant. Okay, so in order to avoid any complexity, we will uh, generalize these constant into dn. We will write dn is equivalent to an multiplied by sine hyperbolic n pi over l minus h. All of these things are constant, so we will use a simple notation dn. So what we get f1x is equal to summation n starts from 1 up to infinity dn sine n pi l over x. Now the idea of the orthogonality of sine waves comes into mind. You can apply the orthogonality condition or this last relation to determine the value of dn. So we will not go into details because we have already discussed this property various time in our previous lectures. So I will directly write the relation part the dn. If you still have any complexity or the orthogonality or the application of orthogonality condition, you can go to lecture number 3 or lecture number 4 and see there that how does we have implemented the orthogonality property. So using that property, I can directly write dn is equal to 2 divided by l into integral from 0 to l f1x sine n pi x over l dx. Now dn, we have generalized dn as a special constant. Dn is basically equivalent to an multiplied by sine hyperbolic n pi over l into minus h. So using the value of dn, we can formulate the quantity en by this integral term. So basically, if you calculate the constant an by this relation and then substitute the values of an in this expression, you will get such a solution that will satisfy all the boundary conditions and the partial differential equation also. Okay, therefore we can write a solution uh, to the second problem as u1 of x is equal to this thing, where the constant an may be calculated by this integral. This is the solution to the second problem. Now the third problem is like del square u2 is equal to 0 with all these boundary conditions. You can apply the same strategy over this problem and you will arrive to solution in such form. Okay, so the solution to the third problem is u2 of xy is equal to summation n starts from 1 up to infinity cn sin n pi over hy into sin hyperbolic n pi over hx. Okay, you can calculate this the solution to this problem by yourself. Okay, here the constant cn will be calculated by this integral. So this is the solution to the third problem. Analogously, we can calculate the solution to the fourth problem also. The fourth problem is del square u3 equal into 0 combined with these set of four boundary conditions. So you can apply the same strategy over this problem and you will arrive at this solution. u3 of xy is equal to n starts from 1 up to infinity dn sin n pi x over l sin hyperbolic n pi over l into y. And the value of dn must be calculated by this integral. So now we have the solution to all the four problems in hand. In fact, we have assumed the solution to the Laplace equation as u of xt is equal to u1 of xt plus u2 of xt plus u3 of xt plus u4 of xt. And we have calculated all these four solutions also. So from these four solutions u1, u2, u3, u4, we can construct the solution to the final Laplace equation. So the solution of the Laplace equation is so much lengthy. U of xy is equal to summation n from 1 up to infinity a n multiplied by this term plus summation n is equal to 1 up to infinity cn sin n pi by hy multiplied by sin hyperbolic n pi over hx plus summation n starts from 1 up to infinity dn sin n pi over lx sin hyperbolic n pi over ly plus summation n starts from 1 up to infinity bn sin n pi over hy sin hyperbolic n pi over h into x minus l. अब आपको ये सोल्यूशन जहन में रखना है, ये सोल्यूशन आपको याद होना चाहिए. इसमें जो कांस्टेंट ए बी ए एन बी एन सी एन और डी एन इन्वॉल्व है, तो इनका हर एक कांस्टेंट के कैलकुलेट करने का अलहदा तरीका है. ए एन को आपने इससे कैलकुलेट करना है, इस इंटीग्रल से. ठीक है. बी एन को कैलकुलेट करना है आपने इस इंटीग्रल से. f1 की वैल्यू आपने यूज करनी है an के लिए, g1 की वैल्यू आपने यूज करनी है bn के लिए, cn के लिए आपने g2 की वैल्यू यूज करनी है इस इंटीग्रल में, और dn के लिए आपने f2 की वैल्यू यूज करनी है इस इंटीग्रल में. दो इंटीग्रल्स है फ्रॉम 0 टू l जो कि x एक्सिस का लेंथ है कि आपका जो रेक्टेंगुलर रीजन है वो इन द डायरेक्शन ऑफ x एक्सिस उसकी लेंथ क्या है. ठीक है. दो इंटीग्रल्स है फ्रॉम 0 टू h. ठीक है. जो कि along the y एक्सिस आपके रेक्टेंगुलर रीजन का जो लेंथ है उसको रिप्रेजेंट कर रहा है. अच्छा, along the y एक्सिस जो इंटीग्रेशन हो रहा है वो विद रिस्पेक्ट टू y इंटीग्रेशन हो रहा है. ठीक है. और along the x एक्सिस जो इंटीग्रेशन हो रहा है वो विद रिस्पेक्ट टू x इंटीग्रेशन हो रहा है. ठीक है. जहां पर विद रिस्पेक्ट टू x इंटीग्रेशन हो रहा है फ्रॉम 0 टू l, तो डिनोमिनेटर वाले टर्म्स में l, डिनोमिनेटर में भी l, और साइन हाइपरबोलिक के न्यूमरेटर आर्गुमेंट के न्यूमरेटर में माइनस h. ठीक है. सिमिलरली यहां पर भी आपको वही सिचुएशन नजर आएगी. 0 टू l l साइन हाइपरबोलिक n पाई और l, यहां पर है पॉजिटिव h, एक h निगेटिव एक h पॉजिटिव. जहां पर विद रिस्पेक्ट टू h y इंटीग्रेशन हो रहा है फ्रॉम 0 टू h, तो डिनोमिनेटर में आपके साथ h है जो कि रेक्टेंगुलर रीजन का y साइड का जो लेंथ है उसको रिप्रेजेंट कर रहा है, और नोमिनेटर में एक इक्वेशन में माइनस l, दूसरी इक्वेशन में l. ठीक है. तो ए एन बी एन सी एन और डी एन आपने इन रिलेशन से कैलकुलेट करने हैं, और फिर यहाँ पर इसको सब्स्टिट्यूट कर देना है. तो जो सोल्यूशन बनेगा वो सोल्यूशन आपका जो लैप्लास इक्वेशन है उसको सेटिस्फाई करेगा. ठीक हो गया. अगर फॉर एग्जांपल कहा जाए कि कैलकुलेट द फर्स्ट three terms of the solution of the Laplace equation, so what does this mean? This will mean that you have to calculate a1 a2 a3 c1 c2 c3 d1 d2 d3, similarly b1 b2 b3, and substitute these equation in this relation. Okay, in order to calculate a1 you have to use n is equal to 1. एल की जगह आपने लेंथ यूज करना है रेक्टेंगुलर रीजन का, एच की जगह आपने ब्रेथ यूज करना है रेक्टेंगुलर रीजन का, और उसी साइड पे जो टेम्परेचर है उसको यूज करना है। यहाँ पर भी n इज इक्वल टू 1 सब्सटीट्यूट कर देंगे तो इस इंटीग्रल को कैलकुलेट कर ले, n इज इक्वल टू 1 के लिए आपको a1 की वैल्यू मिल जाएगी। n इज इक्वल टू 2 सब्सटीट्यूट कर दे, आपको a2 की वैल्यू मिल जाएगी। n इज इक्वल टू 3 सब्सटीट्यूट कर ले, आपको a3 की वैल्यू मिल जाएगी। सिमिलर प्रोसीजर आपने b1 b2 और b3 के लिए करना है, c1 c2 और c3 के लिए करना है, और d1 to d3 भी यही प्रोसीजर आपने अप्लाई करना है। f1 ऑफ x, g1 ऑफ y, g2 ऑफ y और f2 ऑफ x ये क्योंकि नॉन क्वांटिटीज होगी, आपको बताया गया होगा कि रेक्टेंगल के जो एजेस है उन पे क्या टेम्परेचर है, तो ये फंक्शंस आपने वहां से कलेक्ट करने हैं। ठीक है, तो तीन तीन वैल्यूज आप कैलकुलेट कर ले और इन समेशंस के पहले तीन तीन टर्म्स को आप डिराइव कर ले, सो वो फर्स्ट थ्री टर्म्स ऑफ द सॉल्यूशन कहलाएगा लैप्लास इक्वेशन का। अच्छा, एक एग्जांपल मैं आप लोगों को दे देता हूं, पार्शियल u और पार्शियल u बाय पार्शियल t इज इक्वल टू पार्शियल स्क्वायर u और पार्शियल x स्क्वायर प्लस पार्शियल स्क्वायर u और पार्शियल y स्क्वायर। ये जीरो हटा दे, इन स्टैंडर्ड जो लैप्लास इक्वेशन है वो इक्वेशन, और इसके साथ चार बाउंड्रीज पे ये टेम्परेचर्स आपने रखने हैं। एक बाउंड्री पे ये टेम्परेचर, दूसरे बाउंड्री पे ये टेम्परेचर, तीसरी बाउंड्री पे ये टेम्परेचर, फोर्थ बाउंड्री पे ये टेम्परेचर। एच की जगह आप 1 लिख लें। ठीक है, तो यहाँ पर एक कंडीशन है x0 और x1 पे, तो इसका मतलब है कि h की वैल्यू 1 है तो आपने 0 to 1 इंटीग्रेशन करना है। इस तरह x इक्वल टू 0 पे और x इक्वल टू 1 पे कंडीशन, तो इसका मतलब है कि जो रेक्टेंगुलर रीजन है वो असल में स्क्वायर है, एक साइड का लेंथ p1 है, दूसरे साइड का लेंथ p1 है, चारों साइड्स है तो दो साइड्स पे जो टेम्परेचर डिपेंड है वो 0 है, और बाकी के दो साइड्स पे टेम्परेचर एक साइड पे डिफाइंड है x इंटू x माइनस वन, दूसरे पे डिपेंड है y इंटू y माइनस वन। आपने इसी प्रॉब्लम के पहले तीन जो टर्म्स है सोल्यूशन के वो कैलकुलेट करनी है। बेसिकली दिस इज f1 f2 f3 f4 and you have to use these values in this integral term to calculate a n b n c n and d n, and after that you will construct the first three term of the solution. So I think it is enough for today. Inshallah in the next class we will discuss a new topic. So stay home, stay safe. Allah Hafiz.